Hello. So Postgres is 20 years old this year. It was originally released from Berkeley as open source in 1995. So I thought this would be a good year to look back and understand why Postgres is the way it is today by understanding why the features that the developers added over those years were chosen. It's not just what features, though. It's who did it, and most importantly, why. Why were those features the ones that were added, those problems the ones that were interesting to solve? And why not other features? Why not, what were the priorities and the problems that people were interested in solving over that time? And the reason I think this is actually more interesting than it sounds like is to better understand why, what to expect out of Postgres today, and to better understand the decision-making process and the priorities to understand what features to expect in the future. In the in the most optimistic case, if you have a problem with Postgres and you have a feature you need, understanding where it's come from in the past might help you communicate with developers and explain why your problem is the kind of problem that they like to work on. And the underlying theme, the sort of hidden agenda in this talk is to understand that the thing that really drives development over that time and in the future is the problems that users have. Almost all of these features, almost all of these optimizations are driven by complaints from real users. And when you are an administrator and you're considering upgrading to a new version, it's always really easy to look at the release notes and look at all these shiny new features and say, these are all great, but my application works fine without these, and all I see here are risks, the possibility that it's not going to work for me. And all these benefits are things that I don't need. And in reality, I think if you put yourself in the shoes of the admins looking at these older versions, you might start to see that there's risks involved in not upgrading, that you're not going to be the first person to run into these problems. Other people have already run into problems. And you might find, if you choose not to upgrade, you might find yourself a year or two down the line running into a problem, and now you have an urgent situation where you urgently need to upgrade, possibly during an outage, possibly at an inconvenient time, and you could have avoided these problems by letting other people be the pioneers and taking the features and the fixes when they were available. So Postgres, I'm going to review the 20 years of history in about 20 minutes. So I'm going to try and go through this kind of quickly. Ask any questions if I go too quickly. And if I get bogged down in a particular slide, maybe give me a tip. But starting 20 years ago, Postgres was a research project in Berkeley. And this was an era when there were lots of academic projects in different areas. And this was just an interesting time in history when a lot of these academic projects suddenly became relevant to people outside of research. Linux had become popular, and BSD 4.4 was released from Berkeley as an open source package. Software packages like Kerberos and other things from other universities became released as open source, picked up by developers outside of academia. And this was a project described on the Research Labs webpage as more recently, Dr. Stonebraker has managed another project known as Postgres, one of the most advanced such projects ever undertaken on the Berkeley campus. It might be a bit of hyperbole, but it was an ambitious project. And Berkeley might think about updating their lab's web pages because this is actually still up there. Stonebraker had previously worked on Ingress, led the development of Ingress, and this is sometimes a point of confusion. Postgres is not an Ingress fork. There's no shared code in the code base, but there is this sort of shared heritage there with Professor Stonebraker. So the first release of Postgres, Postgres 95, there were a number of features added, but the thing I'm just pointing out here is the copyright that it was released under was the Berkeley copyright, which imposes very few, effectively no restrictions on what you can do with Postgres. So that meant the people were free to create commercial derivatives, forks, and so on. And that's been an interesting experience because the position in the community is that as long as the community Postgres is meeting the needs of its users and addressing their problems, the forks are not a threat. The forks might find niches, they might find, they might make a useful product, but they're not going to threaten the community Postgres. And one day, if Postgres stops addressing its users' needs, then those forks will be valid. There could be a different story. But so far, they've never really threatened, they've never been a negative for Postgres development. It's only been valuable. So this is a difference that between Postgres and some of the other open source databases at the time and still today. And it's been an advantage, I think. Postgres, very quickly at this time, Postgres 95 attracted a large set of developers from around the world, Russia, Japan, all around the world. And they immediately began working on the most important agenda item, the most important development priority of the day. They changed the name. So enough said about that. I'm going to avoid the political issues and focus on the development priorities. The first few releases of Postgres were already adding exciting new features. The people in this image, which might be a bit small to make out, these were some of the first developers. They met together at, actually I think I know where that is, but I'm not going to say. Three of those people, Jan Wick, so two of those people, Jan Wick and Bruce Momjen, were amongst the first people to begin working on Postgres, and they're still involved today. Bruce is here. I'm not sure if Jan is actually here, but he's still very much involved in Postgres development. Tom Lane joined soon thereafter. Tom Lane is on the right there. Bruce is in the front on the left, and Jan Wick is in the back. They, amongst other people, started adding major new features. They, even at this early date, when Postgres was still really only suitable for offline data processing and hobbyist projects, they were adding features like triggers. They were adding features like SQL standard subselects, procedural languages, views. So the interesting thing here is to see how early, even at this early date, Postgres was diverging from the other open source databases at that time. MSQL, MySQL, focusing on low latency, low overhead, very simple queries. Postgres was focusing on subselects and views and joins. The strategy, the design philosophy, even at this date, at this time, was to implement a powerful, sophisticated query language, follow the SQL standard, try and implement the entire SQL standard. And that may have led to a semi-justifiable reputation for having high overhead and startup costs and memory usage, but a lot of that's been addressed and still being addressed today. And machines became more powerful, and as people's needs scaled up, it's served very well. And now those other databases, I think, you could argue, are trying to play catch up, or they serve a different niche. The number of developers and the number of features added in this era is astonishing. There were 180 items in the release notes for Postgres 6.4. Almost all of them could have made this slide. They were all major features. And almost each one was a different developer from the previous, all different names that are unfortunately not still involved in Postgres, but many of them have stuck around. Oleg Bartanov, Peter Eisentraut have been involved almost since the beginning from these early days and are still involved today. Tatsuo Ishii in Japan, Magnus Hagander, they were adding major features at this time. It's actually interesting that at this time you didn't have a user base with huge data and mission-critical databases, so the freedom to experiment and add new features must have been liberating. These days, so much time is spent making sure that new features are not going to cause backwards compatibility issues, are not going to impact reliability, are not going to cause problems maintaining other features or adding other features in the future. Most of the effort today, I find, is spent not solving the hard problem, not solving the interesting problem, but making sure that your solution will not degrade the code quality of Postgres and the reliability of Postgres. So there are actually that map is from the website at the time. It used to be on the Postgres website, and there are pins all around the world for where there are developers. Unfortunately, it's even if it was full screen, the pins are hard to make out on the projector. So continue with that design philosophy of solving hard problems and aiming high with very concurrent design, very high concurrency design and high scalable design. Multi-version currency control was, sorry, my presented software isn't showing me the next slide, so I just keep having to check. Multi-version currency control is not something unique to Postgres, but is unique in the open source world and not very common even in the commercial world. Hot backups via pgdump were obviously something that has stuck around since then and is still very valuable. So Postgres 7.0 was really the first, the major version bumps in the past have been because Postgres acquired some major feature that was considered a watershed feature that would open up major new use cases. So Postgres, I don't know what the discussion at the time on exactly which feature was important to make it 7.0 rather than 6.5, but foreign keys were apparently a major demand, and even the release notes acknowledge this is something that users were demanding. This is something they needed to make Postgres a viable choice in their projects. SQL joins, still major. Sorry, okay. The write-ahead log was added specifically to avoid corruption when the database crashed. And that's, at this point, you can see the goal is still bringing Postgres up to a point where it can be reliable enough with your data to use for business data. Toast is also about solving a user problem that at that time, users found it a major limitation that they couldn't store data that was larger than, I think it was 8K, one page, which was 8K, was the limitation. Toast allows you to and still this design philosophy of solving things in a general, flexible way, transparent to the user. you can store data that's arbitrarily large in a column in Postgres, and this was at the time unique, without having to even worry about how it would work. It would just be storing it outside of your table would just happen transparently to the user. Aiming high like that, instead of just solving things with very manual, programming-intensive approaches, is a unique design of character in Postgres. This last thing, by the way, wasn't a major watershed feature at the time, but in retrospect, it's very important because this is how far back I was able to test old versions of Postgres and benchmark them. Prior to this last point, Postgres didn't support 64-bit architectures. So at the time, that just meant alpha. It seemed like a relatively minor compatible, really nod towards a niche user base running on alphas. And of course, on modern machines, that's everyone. So sometimes things at the time don't look like major deals and end up being more important than you realize. I could have built for 32 bits, but then the benchmarks wouldn't have been apples to apple comparisons. So at this point, the priorities, I have some slides showing benchmarks coming up, so it's not just going to be bullet points like this. I'm sorry if it's seeming like a bit front-loaded with these bullet points. But at this point, you can really see a change in development priority, that now people are using Postgres, instead of adding, people continue adding major features like histograms for queries and so on. But also you see lots of changes that are about scalability and reliability and 24/7 operation. Prior to 7.2, you were expected to run vacuum once a week in a cron job, and while it was running, your tables would be locked. And that was not ideal, but it was seen as a manageable thing to work with for these hobbyist projects, data analysis, personal websites. Businesses had websites, but they were, this was already 2002. So at this point, this was no longer becoming viable, and the pressure was on to solve this problem that vacuum caused an outage on your database. And rather than rip out the multi-version control and the concurrency and the ability to update your database without locking rows, rather than move this work that vacuum does into your transactions, vacuuming was engineered to, this is the much harder approach, much more ambitious approach. Vacuum was re-engineered to not lock tables while it runs. And that's actually a fascinating bit of code to read if you're interested. But it's, the release note boldly claims that now vacuum is no longer a problem. So the later slides might make you doubt that. But all of these version 7 era releases, the features are clearly driven by operational problems that people had as they tried to use Postgres in a live mission-critical website of their business. Things like being able to drop a column on a live database while it's running, being able to, and obviously maintain their schema as it evolves. Being able to, the multi-byte support was actually a major issue because it is one of the reasons that Postgres' adoption in Japan was so high, because it was one of the early databases to support multi-byte encodings from an early date. Vacuum, it turned out, was still a bit of an issue, so there was a new tool called AutoVacuum. So now you didn't have to schedule a cron job and adjust how often it would run. AutoVacuum would automatically detect when your tables had received a certain amount of updates and schedule and start running vacuum for you automatically. So now vacuum's solved. It's not a problem. And at this point, we're actually up to fairly modern history. It's 2005. The interesting thing is how the scale really starts driving the changes. Rather than, the features that people wanted are all there, the reliability was there, and people start really pushing the envelope and building larger databases with more sophisticated data models and more sophisticated queries, and need their 24/7 runtime. So hot backups, point-in-time recovery really changed the game. Now, I think, really now you can take a backup without running pgdump, which means it doesn't need to run queries against your database. You can back up the raw data files from your database and restore it on another machine. And in fact, you can keep restoring the transaction logs on this other machine. And that means you can have a disaster recovery site ready to go at any time. And we know this today, we have streaming replication and so on, but at this point, prior to 8.0, people were running Postgres in production, and all they had to go on were pgdump, which meant that a recovery could take, well, the interesting point is that when pgdump was written, your recovery would take minutes, and that was feasible. But by this point in time, their databases had grown much larger, and now their recovery could take hours or days. And that was no longer feasible. And that's why a hot backup, and of course, when you run pgdump, your data gets reloaded. And you could now discover that, in fact, you had some minor corruption that was a major, possibly caused by an extension or something. And something you should address. But during an outage, when you're trying to do a disaster failover, probably not the time you want to address it. So hot backups mean you have a disaster recovery plan that has the exact same data as your primary, the exact same situation recovered almost byte for byte, and you can have it ready to go on short notice. All of these features driven by scale, driven by changes in what users were doing. So the earlier versions of Postgres worked fine for the users of that era, and now users, as they scaled up their databases, were running into different problems. They're running into index scans that were too slow because their indexes had many, were doing lots of random access throughout their tables, and they wanted to be able to do new styles of queries that were scanning large amounts of data in large. This is the first item there is most useful for like data warehousing queries where you're scanning a large percentage of your table, and you really do need it to run sequentially to get decent performance. So that's the kind of thing that could bite you because you're running in production and everything's running fine today, and all of a sudden your developers try to run a different kind of query, a different type of application, and you find out that actually you need the new version because it solves that problem, and the old version didn't. 2006 was the anniversary meeting in Toronto, and the number of people in this slide are substantially larger than the previous one. This is the first time since that previous slide that many of the developers had met each other face to face. In here you see a large number of people who are still involved in Postgres. Josh is in the front, and I'm not even going to try, but there's all the familiar faces that turn up at conferences and present or are available in the corridors. This was a watershed change in the atmosphere in Postgres. And now instead of being a bunch of anonymous hackers all around the world working for fame and glory, suddenly a lot of there were sponsors for this conference, there were people who were arriving, working for companies providing Postgres support, and from this day there have been conferences every year in Ottawa, and now multiple conferences in the United States and Europe. There were none before 2006. It was a real change in the community. I'm realizing I should have put those benchmarks earlier in the slide, sorry. Being able to create indexes while you're building, while your operations are running, where you're still updating rows, deleting rows, inserting rows. You can build new indexes without interfering with the operations. It's a unique feature that, as far as I know, no other open source database has. The sorting performance changes driven by benchmarks and people running TPCC benchmarks. And being able to run a warm standby database where it continues. This was preliminary work also for hot standby, which is in 8.3 here. I didn't even keep the bullet point. Hot standby, being able to run queries against your standby database. This is something a major commercial database had, but actually Postgres' implementation is even more ambitious, allowing you to run queries while recovery is continuing to run, which is not true for an unnamed major commercial database. The first item here is one of the most enlightening bullet points, because this actually went in actually after feature freeze because it was so urgent. It was such a major benefit. There was a user complaining. So we were used to, so transactions wrap around in Postgres. There are 32 bits, which means you can have 4 billion transaction IDs. And the idea is it does modular arithmetic. So as long as you don't have 4 billion transactions still present in your database, it can wrap around and start back at the beginning. And this all happens transparently. So you don't have to be aware of it, except that you have to make sure that vacuum runs periodically. And 4 billion transactions ought to be enough for anyone. At this point, the scale, and had been enough for almost 10 years, for more than 10 years already. And then someone appeared on the mailing list saying that I'm getting transaction wraparound every 5 or 6 days, which was shocking. We had no idea as developers. It's easy for the developers to get isolated from their user base sometime. We had no idea that there were people running that kind of transaction rate, 4 billion transactions in just a few days. And somebody proposed having, Florian Flug, I think, proposed having, making a distinction between, the only reason they were having such high transaction rates is that some of the transactions, most of the bulk of the transactions did no I/O. They were just read transactions. And so he added virtual transaction IDs, which don't consume any of these persistent transaction IDs that get stored in the database. And so as long as you don't have 4 billion write transactions, which is a lot harder to achieve, you don't have to worry about suddenly the transaction IDs get consumed much lower rate, only by your read-write transactions. And you can see that on the performance benchmarks. So what I did is I actually went back and compiled all these old versions of Postgres using modern compilers, using modern libraries, and ran them on the same machine. So rather than installing old packages that had been compiled using older compilers and older libraries, these are apples-to-apple comparisons on the performance of different versions of Postgres. And I didn't just do it on the major releases. There's almost 180 different Git commits over time. So you can see individual well, not quite individual commits. They're about a month between revisions. So you can see many of the small changes over time. And the major spike, I don't even need the laser pointer here. It's the huge spike in 2011 is this virtual transaction IDs. It's the not having to consume and do disk I/O to record a transaction ID that was only used to do read queries. If there were no updates in your transaction, it only consumes a virtual transaction ID, which is in memory and gets discarded when the transaction finishes. So the difference this makes in performance on the read-only query traffic is huge, as you can see. The transaction rates went from hundreds. You can't even tell from the graph, and I've forgotten what the numbers were. They were on the order of 300 transactions per second, if I remember, to tens of thousands. So on this graph, you see over 60,000 read-only transactions per second if you have 4 clients, and as nearly 100,000 when you have, there's only 8 cores on this machine. So once you get above, the highest here I think was 32 clients, and then above that you get some contention. And the contention, it's this is not an ideal application of having done 180 different benchmarks, but actually there is some interesting things going on here. The older versions are actually there, 7.2, 7.3, they're there, but they're hidden on that lower line near the bottom under later releases because they're very similar. And then the newer releases that have the virtual transactions, you can see the typical curve that you get with parallel operation where there's a peak and when you're running the optimal number of clients. And then above that, you have enough clients to keep all the CPUs busy and you get contention. Unfortunately, this machine doesn't have enough CPUs to really to demonstrate the differences, the improvements in later versions of Postgres. And there have been some interesting blog posts by Thomas Vondra on a much larger machine where you can see the contention at high numbers of clients and see the improvements that have gone on there. The peak at 8 clients is because that's the number of cores in the machine. But I'm really curious about the sharp drop-off after it, and I think there's some interesting research. There's probably a performance bug there that's worth looking into. Also, at this version, there were other major improvements that were driven by experience, driven by users running into problems. Heap-only updates and the auto vacuum improvements are both there to address table bloat. Tables bloat in Postgres because, again, multi-version control is a very ambitious design. It allows a lot of concurrency and a lot of powerful, sorry, my throat. It allows a lot of powerful applications, but one of the things that happens is when you update a record, the old version of the record is still present in your table, and the new version as well. And Vacuum needs to come by eventually and remove the old version, but only once there are no pending transactions in the database that could need to see it to have a consistent snapshot of the database. So heap-only tuples addresses, so your tables grow because they accumulate these older versions. And the goal is that Vacuum will come by at a regular interval and remove them, and you'll have a steady state with a small percentage of your table dedicated to this space for storing the old versions. And almost all of the improvements in Vacuum over time have been about fixing cases where that doesn't happen, and your tables just keep growing and keep growing. Hot updates allow some updates to get cleaned up sooner before Vacuum by other queries the next time they see the page. If you don't update any columns that are indexed, the row can get cleaned up without having to go update remove it from the indexes as well. So it can get cleaned up by other processes at a very low overhead. And that had a huge effect. Very often, very often, your updates are updating only columns that are not indexed, because you typically have keys that you look up data, and the data is the stuff you're updating. And usually, very often, not always, but very often they're separate. The multiple concurrent auto vacuum processes, because prior to 8.3, there would be one auto vacuum process, and it would run automatically when needed. And very often what people found, especially as they scaled up to larger and larger databases, and hardware was changing, use cases were changing, design was changing. So very often what people ended up with were one or a small number of very large tables that received few updates, and a large number of small tables that receive frequent updates. And most of their update traffic would be against those small tables, while the large tables just accumulated log entries or historical data. And auto vacuum would very successfully vacuum those small tables that had frequent updates. When it was implemented, the idea was it would run once a day or every few days. But at this point in time, people might be having auto vacuum run every 10 minutes. The use case, users have the reason vacuum keeps coming up with new problems like this is because users, once one problem are removed, users will push the envelope and find the next problem. And so there will be no end of problems. There will always be interesting problems to solve. So users would, the auto vacuum now at this point would be running every 10 minutes or more often, which was fine, worked fine, until it decided to vacuum the large table that had terabytes of data in it. And while it was doing that, it wouldn't get back to running on the small tables for hours or days. And during that time, they would just expand, fill up with dead tuples, and performance would never recover again after it. So Alvaro Herrera, who is still involved in Postgres today, it sounds like a bit of a refrain, but has added major features since, implemented multiple auto vacuum workers, so that one process could deal with the small tables while that large table was being vacuumed. And that's actually made auto vacuum very much usable for most use cases. I did measure table bloat across 180 versions. The results were a little bit less exciting than you might imagine, because really there have been only a few. Oh, sorry, actually this graph, I only end up graphing the major releases, even though I have 180 revisions, because really there have been only a few major changes to address table bloat. And there's a problem with this graph, which is enlightening in itself. If you look closely at the colors, it actually looks like it was getting worse. 7.3 has moderate table bloat, 7.4 has more, 8.1, 8.2 have massive amounts of table bloat. What's really going on here, of course, is the database is running faster. So the faster the database runs, the more bloat you get. pgbench will just run queries as fast as it can. And that's kind of a typical problem with a lot of these problems. Table bloat really wasn't a major issue early on, because the database just couldn't generate garbage fast enough. But the problem does show the problem getting fixed in the 8.3. In fact, 8.3 is hidden underneath all the later releases on that horizontal line. At this point, well, this is still scaling up because of the visibility map and the free space map. The free space map addressed operational problems that you had to tune these parameters. Postgres spends a lot of, a major priority in Postgres is removing parameters that need to be tuned manually. Every time a new feature is added, one of the big things that people end up spending a lot of time on after feedback from developers is removing the manual tuning, making it work automatically. Because if every feature introduced a new parameter that needed to be tuned manually, the overhead to run Postgres for the administrators would become unmanageable as it grew. The visibility map also is affixed to vacuum. It means it was also useful for index-only scans, so it was valuable in lots of ways. And that was probably what really drove it. But this is also about making vacuum scalable. So now when you have a terabyte table, vacuum doesn't need to scan the entire terabyte table every time it runs. It only needs to scan the pages that have been updated since the last time it ran. And that makes it scale with the amount of update traffic your database receives rather than the amount of historical data you've accumulated. And I'll go through the 9.0 changes really briefly because these are the features that you're really familiar with and so on. But the interesting thing to observe are that these features are no longer about just performance and scaling and dealing with all of a sudden, these features are about dealing with problems that people didn't even know they had previously. Now people want streaming replication and multiple cascading replication and logical replication. They want to be able to do, hot standby, as I mentioned earlier, run queries against the read-only replicas. They need to be able to do an upgrade ideally with 24/7, 24, I've lost my place. These are new experimental, I'd say experimental, but they're new ideas, new features that people want that solve problems they never realized they had in the past. Okay, I'm lying, because per column collational support is actually something people had been begging for many, many years. But synchronous replication is a good example. Like, JSON data types, being able to store arrays were earlier, but now more hierarchical data structures like XML and JSON in the database, index it, be able to perform queries efficiently against complex data structures like that. Materialized views, being able to update through views. These are ambitious features, things that are not just ticking a box for basic operation, but solving problems that people are coming up with new ideas, new things they want the database to do. Most recently, Alvaro added the block range indexes. That's also about dealing with huge tables where just the size of the index mattered. Being able to do upsert is something people had been begging for many years, but rather than implement it in a basic way, Postgres didn't compromise at all on the concurrency and the lack of it's fully concurrent and doesn't have race conditions. So when you run the upsert, you're guaranteed one or the other operation will happen, and you're still not blocking other selects against that same row, and the other selects against the same row still get a consistent snapshot of the database. I think I blew past an earlier slide with the true serializable snapshot mode, and that still works with upsert. Being able to do being able to add these features while not compromising on the concurrency and extensibility and flexibility of early features is something that's been in Postgres' DNA from the beginning, as you saw with the 6.x features already going in. And not going to stop for 9.6. The development work coming in, so 9.6 you'll see in the next talk with Magnus. He's going to go through the new features coming. But what's already being discussed now for 10.0 is mind-boggling. The being able to do parallel sorting and multiple backends to speed up large data warehousing sorts, being able to do multi-master logical replication. The future, the problems don't end. There will always be things to do, but there's so many interesting problems that users will keep coming up with new things that we need to solve. I do have some slides. I'll probably do a lightning talk on these, but just briefly, the running all these, there weren't so many graphs earlier, so I feel I owe you some visual relief. Compiling 180 old versions was an interesting exercise in itself. The bugs that I had to backpatch to get them to compile on new versions was it was interesting to see what problems had been averted by forward-thinking design. The compile times for Postgres went from under a minute to almost 3 minutes. Considering the level of complexity and sophistication that's gone in that time, that's actually surprisingly small change. The binary has grown over that time from about 2 megabytes to about 5 megabytes. When people accustomed to C++ and Java binaries find out that all of Postgres is only the binary is only 5 megabytes, they sometimes get a bit confused that surely that's gigabytes or no. To be fair, a lot of the stuff like the encoding tables actually are now in loadable modules, so the entire database install is a bit larger than that. And that's actually the reason for the big jumps and drops is the encoding tables were moved from being inside the binary to being externally loaded. And lastly, this is one of the reasons for the performance drops. The tables themselves were stored more densely. There were 2 major improvements in that area. So there's a few minutes for questions, and I know those slides are hard to interpret, so if you have any questions, I can try and explain some of them.
How much time did you spend compiling this?
It was about 2 weeks. It was an interesting experience because, so I wrote a script to do it, and I accumulated a directory full of patches. And the script just goes through all these patches and just tries to apply them I don't try and keep track of which patches are needed for which version, it just tries to apply them all. And basically I would get far enough back, I'd get like a few years back, run into a problem, figure out what needed to be backpatched or fixed to get it to compile, add that to the directory, and run it again, and it would get another year back, run into another problem. And then I got back as far as the support for 64-bit architectures, and that's when I just drew the line. Some of the fixes were astonishing. Like some of these fixes were really interesting. There were things. Most of them were easy. Most of them it was just a matter of looking at the mailing list and finding out the commits that I just passed over, and finding the commit that fixed the problem. So they would be things like the new version of GCC requires, that doesn't allow us to do 0-byte arrays. There's a new syntax for variable size arrays. So I had to backpatch the commit that had that fix. But some of them were actually things that were that were fixed prior to being problem. So I wasn't able to always find the commit, and I had to figure out what was going wrong and debug it myself. And once I had done that, then I was able to find a commit where usually Tom had said, I think we should do this to future-proof against possible problems. And it turns out more than once I ran into situations where he was dead on right, and there was later tools didn't work with the old way of doing it. So it was really interesting to see like the engineering, forward-thinking engineering, solving real problems that I'm not sure he even realizes like that those decisions had real ramifications like that later. Yes?
The graph that you had that showed performance over time for that one, that purple line.
Yes.
Right is the second from the bottom. Do you know
So that's the same as that peak on the left there. That's the difference between, so the purple line is 8 clients. Oh, why it dropped. Yeah. So that's the same as that peak on the left there, and then you see later versions don't have that peak. They just go smoothly up. So I'm curious as well what changed, why there used to be, and it's consistent. It's not just like one version performed quirkily. I mean, these were run multiple times, and this is the median, so shouldn't have a problem like that. But in any case, this is multiple revisions that had this peak in performance at 8 clients that goes away above 8 clients, and then later versions, as you can see, like here, later versions, that peak goes away. So I'm definitely curious about that, but it does have, it has to have something to do with the fact that that's how many cores the machine had. So it's, I don't know why it would have gone, I'm very interested myself in why that changed. And the later performance makes a lot of sense. This is a nice smooth curve. So yeah, that is strange. I think this might be the last question.
One quick one. Did you spend much time working out the configurations across all those different versions for some kind of a baseline for these tests?
So I use the default config. So one of the things this is showing is that the default config has changed over time as well. The only things I changed so I didn't want to do things like tune auto vacuum because I wanted to show that auto vacuum now doesn't require much tuning. I did raise the amount of shared buffers so that I was using most of the memory of the machine. And I think I set the checkpoint timeout so that it wasn't doing checkpoints because pgbench does a lot of I/O. But other than that, it's the default config. Okay. Thank you very much. I look forward to seeing Magnus's talk on the elephant's trunk and see the directions for the future. Thank you.